Okay, so welcome back to the video. So here we have an improper integral from negative infinity to infinity of e to the negative x squared times 5x squared plus 2x to the fourth, all this being divided by x squared times x squared plus 1 dx. So we have a Gaussian function involved, and we also have a bunch of polynomials multiplied / divide alongside with it. So it's actually not that bad. It looks tough from a first glance, but through some algebra and calculus, I say that a lot, that it does indeed come down to a nice result. So throughout that process, you're going to see that we're actually going to cover into another different math topic that will be used to solve this improper integral. That's nice. And a couple of, as you notice, there's the Gaussian integral with e to the negative x squared. So there will be some value usage into that implemented to it as well. And there's also two more functions that we'll be using that I don't think I've really covered too much about, but it's been used in a couple of my videos, but those will be along the way. So expect some of that. So let's have some fun and let's just jump right in. Start off, we're going to call this capital I, but we're actually going to be doing some bit of a clever trick to make the simplification a little bit nice. So what I'm going to do here is, we had noticed that we have an x squared plus 1 on the denominator. So what I can do from here is we're actually going to add and subtract a negative x, we're going to add and subtract an x squared. So what this is nice is that when we actually apply the linearity to it, that it'll actually cancel out some stuff from the denominator. So what we'll have is the Gaussian integral e to negative x squared, then 5x squared plus 2x to the fourth. Then this is all being multiplied by x squared plus 1 and then minus x squared. So again, it's the whole multiplied by 1 and then rearranging that to a different sense. So x squared then times x squared plus 1 and then all this being multiplied by dx. Okay, as I mentioned, we're going to see that if we just apply some linearity with the distribution, then we're going to have something from the denominator that will cancel from each one of the terms. So reducing all this out, we're going to actually have the difference of two improper integrals. So negative infinity to infinity. So the first one we'll have is e to the negative x squared. So 5x squared plus 2x to the fourth. So our denominator in this situation for now is going to be x squared. Meanwhile, after doing that, then we have the subtraction from over here, and now get rid of the x squared. So now this is going to be the same numerator on the top, and now our denominator this time is going to be x squared. Add this with 1, and then multiply with dx. Cool. So with this, now let's actually take our focus into this part of the integrand over here. We'll leave this by itself for now. We'll come back into it eventually. So that means for now, applying that distributions, I have a 5x squared then divided by the x squared, so that'll cancel out, and then I have a constant, so I'll just factor that outside. So I have 5, and then multiply with negative infinity to infinity of just the Gaussian integral itself. I think we know what value that comes down to, but let's slow things down just a bit before we continue further. Do the same thing over here, x to the fourth divided by x squared, so that's just x squared on the top, and I'll factor out the 2 from there as well. So now it's plus 2. Then multiply with the integral. So this will be x squared then times e to the negative x squared and then dx. And then of course now subtract with just this integral over here that we have saved for later. Let's pay attention to this integral over here. For right now, we don't really want to focus on the Gaussian function. What we really want to pay attention to is the 5x squared plus 2x to the fourth and then divided by x squared. So saving you all the trouble, what you'll need to do here is apply some long division. And so therefore after, and you can do the verification yourself. So apply long division. We'll have that 5x squared plus 2x to the fourth divided by x squared plus 1 is simply just equal to 2x squared minus 3 or plus 3 and minus 3 divided by x squared plus 1. So again, we can actually just multiply all this through together, and now we'll actually get a new following for I. So now I is going to be rewritten as, so the same two are going to stay the same. And so from here, we just replace everything back here from that whole 5x squared plus 2x4 divided by x squared plus 1, new substitution, and just distribute the e to the negative x squared, the Gaussian function, into everything here. And again, we can apply the linearity with the integrals as well. So now we'll have a subtraction, so subtract, well, factor out the constant as well, since that's important as well. So I have 2, then negative infinity to infinity of x squared e to the negative x squared, and then times dx. Okay, continuing forward, so then I'll have now, this is going to be subtract 3, then multiply with negative infinity to infinity of e to the negative x squared dx. And then the last one we have is the minus 3x squared plus 1, but distribute the negative from over here, so now become a plus. So this means now plus, factor this out, so I have 3, then multiply infinity, negative infinity of e to the negative x squared, and then divided by x squared plus 1, and then multiply with dx. Okay, so continuing forward, there's some things that can actually be simplified and cancel out. As we see, these two share the same integrand, and then this by term, so they cancel each other out. I have a Gaussian integral over here and a Gaussian integral over here, so take the difference of those, so now it's just going to be 2 times that. So 2 times negative infinity to infinity of e to the negative x squared, and then dx, and then all that's left is just that last term over there. Now that's straightforward to see that this is the Gaussian integral over here. We know what that value is. It's going to equal the square root of pi. I did a video on this a long time ago, so if you want to check that out, I'll leave that link in the description below. So as mentioned, that's the square root of pi. And then another thing we can also do for over here, let's actually define a function so we can actually find a generalization that eventually will come down to. So let me put define. So I'll call this function, we'll call it f of alpha. So we'll say let that equal to the integral from infinity or negative infinity to infinity of e to the negative alpha x squared, and then divided by 1 plus x squared dx, or x squared plus 1, however you want to. It's addition, so it's okay. So with that, let's put that in mind. And then so far, to put things in perspective after we actually put our values, so far we'll have that this is 2 times the square root of pi, and then plus 3 times f. But if we actually plug in alpha equals 1, that actually matches over here. So what's left here is we have to calculate what f of 1 is equal to, but exactly. So with that, let's actually move on to that next step. So next, what I'll do here is our f of alpha function. Let's actually take the derivative of that. So Feynman's trick, of course, I can differentiate inside of the integral. So putting all this, that means this is, so for one, we'll get a negative factor, so I'll put that outside, so it's negative. So infinity, negative infinity, and we take the derivative of that exponent, so that means this is going to give us x squared, with of course with respect to alpha. So actually no, that's fine the way it is. So that's x squared, then e to the negative alpha x squared, and then divided by 1 plus x squared, then dx. Okay, and so what I can do here is if I take a look at the quantity for x squared, I can actually add and subtract a 1. So what's nice is that I can actually cancel out something from the denominator and leaves us with another part of the integral. So with that difference and using linearity, and so doing so, we'll have that this simplification from there we'll have is the negative infinity or negative infinity to infinity of e to the negative alpha x squared dx, and then we're going to add this with negative infinity to infinity of the same things. Well, rather it's 1 times that, so e to the negative alpha x squared, and then 1 plus x squared, then dx. Interestingly, what's nice is that this is actually the exact same function as our f of alpha, so that means I can substitute that and say that this is, over here, this is our f of alpha function. So let's put that into our substitution over here. And so, interestingly, so now I have that so far f prime of alpha, and what I can do is I'll actually just set this integral by itself, but that actually comes down to a nice closed form that I'll write in a second. That again, that's the general closed form for finding the Gaussian integral. I'll subtract this minus f of alpha function over here, and so on the right hand side for here, this is actually going to equal to the generalization of pi divided by alpha. So as we see here, and as I mentioned before, there's another topic that we're going to be using in differential equations. And as you can see, this is actually in the form of a first order linear equation. So how this works is that we need to find the integrating factor, multiply that integrating factor to both sides, then take that integral, and then eventually we'll have to find the constant that we need to find in order to find that equation. And then eventually this will lead us to how we want to find our f of alpha function evaluated at the end, that we can actually just substitute the value for alpha and again get the final answer that we would need to achieve for. So continuing forward, this is a first order linear equation. So again, use the integrating factor, so mu of alpha, so that would equal to e, and then to the integral. So in this case, this is associated with -1. If you learn this as your p of x or p of alpha, whichever the function. And then on the right hand side is your q of alpha function. So this is negative du or d alpha, and then this is going to equal to e to the negative alpha over here. So that means I just have to multiply e to negative alpha to both sides. So continuing forward over here, so e to the negative alpha, then times f of alpha minus e to the negative alpha times f of, well, this is a prime over here, and then this is just the regular function f of alpha, then multiply here. So I have now, this is going to be negative square root of pi, and then times e to the negative alpha, and then divided by the square root of alpha on the bottom. Okay, so from there, now, this is not really the issue. What we really need to do is now take the integral of both sides, and then this is actually what we need to continue forward. This, if you integrate this side, this actually just undo everything, gives you the product rule. So that's the least of our worries, but we need to figure out the right-hand side. No worries, we can actually just use a u substitution. So let me actually use a different color for this. As for the u sub, we'll let u equals, in this situation, we'll let that be negative, or not negative, we'll let this be the square root of alpha. Then what I'll do is differentiate both sides. Well, let's actually solve for alpha on its own, because eventually we're gonna have to place that back on itself. So doing so, we have u squared is equal to just alpha. Okay, so from here, then differentiate both sides from here. So that means 2u du is equal to d alpha. That's nice that I can actually just plug that substitution back in. So skipping this step, just integrating this both sides, that's the product rule. Integrating that, that's the derivative. So we're actually just left with just e to the negative alpha, and then multiply with f of alpha. So that's out of the way. So that means now, let me factor out the negative square root of pi of outside, integrating this. So that's gonna give us, let's see, so e to the negative alpha. So that's e to the negative u squared, and then the square root of alpha out there. So that means that's divided by u. Then with this 2u du, the u's would cancel from both the numerator and denominator. And I could actually factor out the 2, but let's take things one step at a time. So this will leave the 2 here, then e to the negative u squared, and then du. So from here, that means, in other words, now I'll just take things another step ahead. So this is negative 2 times the square root of pi, and then multiply with the negative u squared du. Keep in mind, for something like this, you want to realize that there is actually not exactly an elementary function that actually, comes down, that has its own antiderivative. Now, where it has the bounds, then there might be some way to solve this, and hence we wouldn't have the Gaussian integral to begin with, but we have no bounds, so this is an indefinite integral. No antiderivative exists in that situation, but we can actually fix this up. So keep in mind that the definition we'll be using is the error function. So the error, and that's why I mentioned where the error, where some functions are going to come in handy for this situation. So for error function of t, by the integral definition, it's equal to 2 divided by the square root of pi. Then we multiply from 0 to t of e to the negative u squared, and then du. So what if I were to take the derivative in respect to t? So d and then dt of the error function of t. So really, this just gets rid of the integral, but we also have to do integrate this. This is hence by fundamental theorem of calculus. So it's 2 divided by the square root of pi, and then multiply with e to the negative t squared. Okay, so that's our derivative over here. So now we can actually just solve this out by, now let's say if I just divide the 2 divided by the square root of pi from both sides, and then if I were to take that integral, so that means the integral from the square root of pi divided by 2 of the derivative of dt, and then the error function of t. That will be the same thing, let's see, dt, and then that will be the same thing as saying taking the integral of e to the negative t squared, then dt. So that's nice to say that therefore we see that the integral of e to the negative t squared, well, I'll put this in a situation so that we're dealing this with u. So e to the negative u squared du is going to equal to the square root of pi, and then divided by 2, multiplied by the error function of u, and then plus c. So with that can actually go into that substitution over here. So if I substitute everything back into here, then that means so far I have that e to the negative alpha, then times f of alpha is going to equal 2. So multiply the negative 2 times square root of pi 2 over here. And so that will just yield us negative pi, then multiply with the error function of u. But in this case, we have that u is equal, we said u equals the square root of alpha over here. So I'll just replace that back in. And then last thing to do is just add our c, since it's some arbitrary constant. Okay, so we're actually almost there. So now multiply the e to the negative alpha to, or divide the e to negative alpha to both sides to just get our standard f of alpha function. So that yields us with negative pi, then e to the positive alpha, the error function times the square root of alpha, and then add this with c times e to the power alpha. Okay, so a couple more things left. So there's some things to note that if I were to plug 0 into our f of alpha function, so that means I have that e to the negative 0 and all that, that means that's going to be 1. Then so that'll yield us with 1 divided by 1 plus x squared. The antiderivative of that is arctangent of x. So put in the infinity over negative infinity as the approaches. We'll have that this is pi over 2 subtract negative pi over 2, and that's actually going to give us pi. So therefore, we see that, I'll put this on the side over here, f of 0 is equal to just pi. So if I were to set this up and plug this back in, so if I plug in 0 for alpha, so that means pi is on this left-hand side. If I plug in 0 over here, so that means this is going to be 1. And if I plug in 0, the error function of 0 is actually just going to equal 0, so that vanishes. So over here, e to the 0 is 1, so that means all that's left is that c is equal to pi. And so that, let's actually just plug in all this back in. So now that'll yield us that f of alpha is going to equal to just negative pi, then e to the power alpha, then the error function of square root of alpha, and then add this with pi times e to the alpha. Now let me erase this part of the board and make some room for the rest of the work. And so what's nice is that if I were to plug 1 for alpha, so 1 is over here, e to the negative x squared, and then 1 plus x squared. That's exactly this function that we wanted to calculate, the f of 1. So that's the last thing we have to do, just plug in 1, and then we just have to calculate what this whole thing is, just do the simplification and distribution. So if I plug in f of 1 back into here, so if I just substitute 1 for alpha, so I have that f of 1 is going to equal to negative pi and times e, then multiply with the error function at 1, and then add this with pi times e. Interestingly, I can factor out a pi times e over to both sides. So pi e, then multiply with, now it's just 1, and then to subtract the error function of 1. And what's nice is that this is actually a nice identity. Well, if I just substitute the 1 for just a variable, by definition of the complementary function error, I have that ERFC of t for some variable t is equal to this entire thing, replaced with the variable. So therefore, to put this simply, I have that pi e and then multiply with, well, let me get rid of that parentheses. This is pi times e and then written as ERFC of 1. And so that actually completes our f of 1 function. So substitute this back in. And so therefore, the final answer is that I is equal to just 2 times the square root of pi, multiply with 3 f of 1 over here. So that means plus 3, then times pi times e, then times the complementary error function evaluated at 1. And so therefore that actually completes the improper integral evaluation just like that. So a lot of things going on. We have, just your standard calculus and your algebra. We have the long division, and we actually have a topic with differential equations with the first order linear equation implemented into this problem solving. So there you have it. So yeah, that's pretty cool if you ask me.